So remember from algebra, continuity is if you have to pick up your pen while drawing a graph, then it is not continuous. This is our first topic after limits, and we're going to see why we did limits first because we use them for continuity. But at the end of the day, even though we're learning calculus, we want to go back to algebra. If you pick up your pen, it's not continuous. So we're going to get into this formal definition of continuity. And instead of just saying, well, I picked up my pen, so it's discontinuous, we're going to be fancy calculus students and we're going to say why it's discontinuous. So the reason why something is discontinuous is because it fails something on this continuity checklist. So we're going to write the three things. I usually call it the continuity checklist. They're the three things that make something continuous. So a function f is continuous at a number c if the following conditions are satisfied. So the first thing that has to be satisfied is f of c is defined. That means when you plug in the x value c, it has a y value come out. It's a fancy way of saying it has a y value. You can plug it in and you don't get undefined or an error on your calculator. You get like 17. You get a number out. Okay, so if you can plug it in, there's the first sign it's continuous. It doesn't make you divide by 0 or take the square root of a negative. You're good to go. So second thing that you would check to see if something's continuous is if it has a limit as x approaches c of f of x. That limit, in order for it to be continuous, has to exist. Think about it. If you come in from the left and the right and you get to two different numbers, then it's definitely not continuous. So this limit has to exist. You have to get to the same number from the left and the right in order to be continuous. And really, it has to be finite. Because we've seen the limit be infinity, and you really can't draw that without picking your pencil up. So you'd say up and then up, but you're still picking up your pen to draw something that has like a limit of infinity. So when it exists, it has to be finite in order to be continuous as well. There's a longer way of writing this rule, and I'm going to write it over here. They're the same thing, but you'll see it in the text, and on WebAssign we're in this is the shorter way, and then the longer way is to say that the limit as x approaches c from the left side is the same thing as the limit as x approaches c from the right side. It's a longer way of saying the limit exists. Your left-hand limit is the same as your right-hand limit. Longer way of saying the limit exists. So you'll see it both ways. So it has a y value and it has a limit. Our third thing on our continuity checklist is that our y value, what we get when we plug in f of c, is the same thing as our limit. So it has a y value, has a limit, and they're equal, is what that third property says. Those are three things on our continuity checklist. You check, does it have a y value? Does it have a limit? Are they the same thing? Okay? So when they're not continuous, we get types of discontinuity. And we're going to look at three types of discontinuity. And they're types of discontinuity because they fail one or more of the properties above. Okay, as long as they fail one, it's discontinuous, but some of them will fail more than one. So we're going to have three types of discontinuity. I'm going to list them in order from like the easiest to find to the hardest to find. So I think the easiest one to identify is infinite. Infinite discontinuity is kind of obvious why it's called infinite. It's because the limits are going to infinity. This looks like a vertical asymptote. It is a vertical asymptote. That's what it looks like. If you're looking at something and you're like, hey, that's a vertical asymptote, what you would call that is an infinite discontinuity. So it would be something like this, where the left-hand limit is infinity and the right-hand limit is negative infinity, and there's an infinite discontinuity. Also, it can look all the other ways a vertical asymptote can look. We can draw them here, both up, up, or down, down, or maybe the other way where they're opposite, where it's down, up. Those are infinite discontinuities. They're the vertical asymptote. The limits are going to infinity, and that's how you get the name infinite. The next two types of discontinuity kind of get confused every semester, but their names say what they look like, I think. So they're easily confused, but maybe I would say removable is the next easiest to identify. Both of them are kind of tricky at first. Removable looks like a hole. It is just a little hole in the graph that can be removed. That's how it gets the name removable. Looks like a hole in the graph that you could just fill in and then you'd be continuous. So something like this. All I would have to do to make this continuous is color in that one hole, and then I wouldn't even have a discontinuity. So it's easily removable, and that's how it gets its name. Our last type of discontinuity is called a jump. This is where you jump from one graph to another. So it gets its name because you jump from one piece to another. One part of a graph to another. So something that's jump could be this. So for some reason it gets confused with removable, I guess because infinite is just so obviously it's like its own thing because the limits are infinity. Removable is you fill in the circle and you've gotten rid of the discontinuity. Even if I fill in this circle, it's still going to be discontinuous. I would have to jump this whole piece up or jump this entire piece down in order to get rid of the discontinuity, and that's why it's called jump. So we want to note some patterns when we don't have a picture is that all blank functions are continuous for all x values, and the answer for that is all polynomial functions. All polynomial functions are continuous for every x value. So a polynomial is something like x squared plus 5x plus 2, something where it's just x to a positive power added or subtracted together. So we can give ourselves an example. X to the 5th minus x cubed plus 6x. Something like that. That's going to be continuous everywhere. Nothing makes you divide by 0 or take the square root of a negative number. There's nothing illegal that's going to happen there. A rational function, rational is a fancy way for saying a fraction function. A rational function which has a numerator that may or may not have x's and a denominator that may or may not have x's is going to be continuous everywhere except for where? What can't happen? The denominator can't be what? It cannot be 0. So it's going to be continuous anywhere where the denominator is not 0. And we'll use that when we get to doing these without a picture. First, we're going to look at pictures and use our continuity checklist, identify our discontinuity, and then we'll use this when we look at just some functions.